Good morning, Namaskar. Am I audible? In the last class, we started to study about the magnetic properties. Let us go ahead and we studied a few magnetic materials. I think this was the last point which we discussed. This is a paramagnetic material. So let's start discussing about the ferromagnetic materials. So next studying is ferromagnetic materials. These materials also contain dipoles, and these dipoles are parallel to each other. They contain dipole and dipoles are parallel to each other. Because of the parallel arrangement, even in the absence of electric field, you will get non-zero magnetization. So in the absence of field, whatever magnetization you get, that is known as spontaneous magnetization. So these materials will exhibit spontaneous magnetization. When you apply magnetic field will apply torque on these dipoles, and because of that torque, all of them will rotate along the direction of field. So you will get very strong value of magnetization on the application of field. So susceptibility will be high and positive value. When you remove the field, still they are parallel to each other. So even after removal of field, you are going to get certain non-zero value of magnetization, and hence they will exhibit spontaneous magnetization. All these things are happening because these dipoles are parallel. So if you start increasing the temperature, randomness in dipoles increases, and they will reach up to a certain temperature. Let us suppose Curie temperature. At Curie temperature, dipoles will become extremely random. So the material will start behaving like para-electric material. So the significance of Curie temperature is that below the Curie temperature, material behaves like ferromagnetic, and above the Curie temperature, material starts behaving like paramagnetic, because all the dipoles become randomly oriented at the Curie temperature. So you can use these materials for your application purpose only below the Curie temperature. Above the Curie temperature, they are weak magnetic material, means they are paramagnetic materials. So Curie temperature becomes very important for them. The most common example for this material is iron. Iron is ferrous, and that's why the name is ferro. Curie temperature for iron is 1043 Kelvin. 770 or 768 whatever centigrade, whatever value you get in the exam, you can use it. Then second one is cobalt. Cobalt is 1404 Kelvin. And the third one is nickel. Nickel is 631 Kelvin. These three are very important, so you need to remember the value of Curie temperature as well. Remaining you can name only, like GD. GD is gadolinium. This is also a ferromagnetic material. And then dy is dysprosium. And these all are examples of ferromagnetic material. There can be several other ferromagnetic materials also. So please note down these examples, then I would be dictating few points. लिखेंगे. Let's start writing. These materials contain materials contain parallel arrangement of dipoles, parallel arrangement of dipoles, arrangement of dipoles. These materials get strongly magnetized on the application of magnetic field, on the application of strongly magnetized on the application of magnetic field. And remain magnetized even after the removal of field, even after the removal of field, removal of field. The value of magnetization even in the absence of field, the value of magnetization in the absence of field, absence of field is known as spontaneous magnetization, spontaneous magnetization. These materials exhibit hysteresis curve. These materials exhibit hysteresis curve. Hysteresis curve. These materials remain ferromagnetic. These materials remain ferromagnetic up to Curie temperature. And above Curie temperature, and above Curie temperature, they start behaving like paramagnetic material. Paramagnetic material. This is few important things related with the ferromagnetic material. Please note down it quickly. Yes, it is first slide. Rishabh. Now, ferromagnetic domain wall theory, ferromagnetic domain wall theory and hysteresis curve. Ferromagnetic domain wall theory and hysteresis curve. Let us suppose we take up fresh ferromagnetic material. When I say fresh ferromagnetic material, virgin specimen of ferromagnetic material. It means this material has never been subjected to magnetic field in its life. ऐसा मटेरियल जो अपनी लाइफ में कभी भी मैग्नेटिक फील्ड को सब्जेक्ट नहीं किया गया है. ठीक, दिस इज द मटेरियल व्हिच हैज नेवर बीन सब्जेक्टेड टू मैग्नेटिक फील्ड इन इट्स लाइफ. ऐसा मटेरियल जो कभी भी मैग्नेटिक फील्ड को सब्जेक्ट नहीं किया गया है. Right? This is the ferromagnetic material that is known as virgin specimen. In this specimen, there are a number of regions. Each region is known as domain. And the wall separating to these regions is known as domain wall. In a particular domain, all the dipoles are parallel to each other. But domain to domain, orientation of dipoles is different. In a particular domain, all the dipoles are parallel to each other, but domain to domain, orientation of dipoles is different. किसी एक डोमेन में सभी डायपोल्स पैरेलल टू ईच अदर हैं, बट डोमेन टू डोमेन डायपोल्स का ओरिएंटेशन डिफरेंट है. Material is in multi-domain state. It has multiple domains. I am not able to show all the domains. I am showing some of the domains. So this is the multi-domain state of material. Multi-domain state. This is multi-domain state. So material is having multiple domains. So this is your virgin specimen of ferromagnetic material. If you see any particular domain, all the dipoles are parallel to each other. So that domain is magnetically saturated. But when you see as a whole, the whole material, so orientation of domain to domain is different. So they will cancel each other and hence net magnetization will be equal to 0. Right? So initially in the absence of field, all these domains will cancel each other. So net magnetization is 0. We are wanting to draw a curve between the magnetization versus magnetic field. M versus H या B versus H भी same आएगा, क्योंकि when you will apply magnetic field, magnetization will take place and that will result into the magnetic flux density. So magnetic flux density versus applied field या magnetization versus applied field, the curve will remain same for both of the cases. So this is the curve which we are wanting to draw. Now initially we are at this point here. We are here. Let us suppose point A. No magnetic field applied and no magnetization. Although in a particular domain all the dipoles are parallel, that is magnetically saturated, but domain to domain orientation is different, so they will cancel each other. So this is the structure of material corresponding to point A. Now suppose I start applying magnetic field. Let us suppose the direction of magnetic field is this. So the domain which has dipoles angle wise more closer to the direction of magnetic field, that is known as favorable domain. If field was like this, then this would have been favorable domain. If field was like this, then this would have been favorable domain. Since field is like this, so this is the most favorable domain because it is very closer to field direction, most favorable domain. Now I am taking this domain as reference to explain the phenomena. So we are initially assuming this as the reference. When we apply the magnetic field will apply torque on the dipoles. So these dipoles will start to rotate. But since all the dipoles in a domain are parallel, so when they will rotate, it will seem that the whole domain is rotating. This phenomena is known as domain wall motion, because when dipoles will rotate, it will seem that whole domain is rotating. So domain wall would be rotating. So domain wall motion. Because of this domain wall motion, these dipoles will try to come towards the most favorable domain, and because of which the magnetization will increase. So with increase in magnetic field, the magnetization will increase. Initially, this increase is linear. This increase is linear. Initial value of this increase is linear. This is linear. What does linear signifies? Linear signifies that if you apply magnetic field, you will get non-zero magnetization, and if magnetic field is zero, magnetization will become zero. So on the application of magnetic field, you are getting certain value of magnetization. On the removal of field, magnetization is zero. That is the meaning of a linear curve. What does happen here? You apply magnetic field, these domains will rotate towards the most favorable. But when you remove, they will return back to their original position. Then only the magnetization can become zero. It means reversible domain wall motion is happening. You apply the magnetic field, domains are rotating. You remove the magnetic field, domains are coming back to their original position. मेरे जो सिविल और मैकेनिकल के मित्र हैं वो ऐसे समझें कि स्ट्रेस स्ट्रेन डायग्राम में इलास्टिसिटी के पॉइंट तक जिस तरह से मटेरियल का बिहेवियर होता है कुछ वैसा ही है. इट इज कि व्हेन यू अप्लाई फोर्स देन मटेरियल इज स्ट्रेन्ड, एंड व्हेन यू रिमूव द लोड देन मटेरियल गेट्स ओरिजिनल पोजीशन. सिमिलरली हियर द फोर्स इज व्हाट? हियर द फोर्स इज मैग्नेटिक फोर्स. सो व्हेन इट इज अप्लाइड द डोमेन्स रोटेट एंड यू गेट मैग्नेटाइजेशन. व्हेन यू रिमूव द मैग्नेटाइजेशन vanishes, means domain walls return back to their original position. So you can say that this region of the graph represents reversible domain wall motion. Reversible domain wall motion. It is reversible domain wall motion. Now, if we keep on increasing the field beyond point B, then magnetization increases, but it becomes non-linear curve. It becomes non-linear. What is the significance of non-linear? Non-linear means even if we make the magnetic field zero, still we will get certain non-zero value of magnetization. So in the absence of magnetic field, you will get non-zero magnetization. That means some spontaneous magnetization will take place. आइए इसको explain करते हैं कैसे यहाँ पर. So when we start increasing the magnetic field, then with increase in magnetic field, these domains rotate towards the most favorable domain. हमने उसको reference लिया है. So size of most favorable domain grows and remaining domain become smaller. This is known as domain growth. Even if we remove the field, these domains are not able to return back to original position. Hence, a permanent domain growth has taken place in the material, and the most favorable domain has grown in the side. So when we start increasing the field, then size of the most favorable domain starts growing, and remaining domain स्टार्ट श्रिंकिंग. बाकी के डोमेन का साइज श्रिंक होता चला जाता है, या दे कीप ऑन वैनिशिंग, या वो गायब होते चले जाते हैं. सो दिस इज रिप्रेजेंटिंग डोमेन ग्रोथ. डोमेन ग्रोथ या डोमेन एक्सपेंशन. इट इज आल्सो नोन एज डोमेन एक्सपेंशन. मोस्ट फेवरेबल डोमेin is expanding. Here irreversible domain wall motion is happening. No domains are returning back to their original position. If you keep on increasing the magnetic field, then all these domain walls will collapse and material will, let us suppose this is somewhere point B, and we keep on increasing the field, then we will reach to point C, and at the point C all the domain walls will collapse and material will convert from multi-domain to single domain state. So at certain point, let us suppose that is point D, and at point D all the domain wall has been collapsed. It is point C, लिख लीजिए इसे, it is point C, and it is basically this is point between point B and C, B and D. This is point between point B and D. This is point D. Here the material has converted into single domain state. Your material has converted into single domain state. So let us suppose this is our point D, and here we have got the single domain state. This is the single domain state. Up to this point, irreversible domain wall motion happened. Irreversible domain wall motion, that is also known as domain expansion. Domain expansion, basically favorable domain का expansion हुआ, so it can be also said as domain expansion. If you increase beyond this point, then there is no domain. So domain wall motion is finished. Now you have single domain. So on application of magnetic field, still magnetic field will apply torque on the dipoles. So dipole rotation will start to take place, and these dipoles will keep on rotating until all of them get parallel to the applied magnetic field. Once the dipoles become parallel to the applied magnetic field, you will get maximum value of magnetization. This maximum value of magnetization is known as saturation magnetization. So this is basically saturation state. So point D के beyond domain walls खत्म हो गई हैं. Now dipole rotation will take place, and it will take place till the dipoles become parallel to each other. So it will keep on happening till the dipoles become parallel to each other like this, and parallel to the applied magnetic field. At this point we will get maximum value of magnetization. This maximum value of magnetization is known as saturation magnetization. Saturation magnetization. No benefit of further increasing the field. Even if you increase the field further, it will remain constant. You will be getting the same value of magnetization. So stop increasing the field. From these point D to E, let us suppose this is point E. So from D to E, dipole rotation takes place. From D to E, dipole rotation takes place. Now once we start decreasing the field, no benefit of further increasing the field. So if we start decreasing the field, then magnetization will keep on decreasing. It will keep on decreasing, and at certain magnetic field, let us suppose magnetic field becomes 0, still we have certain non-zero value of magnetization. I am representing it with MR. So it is known as spontaneous या residual magnetization. Spontaneous or residual magnetization. This is known as spontaneous or residual magnetization. To make this residual magnetization 0, the magnetic field applied in the reverse direction is known as coercive field. The amount of field required to be applied in the reverse direction is known as coercive field. It is known as coercive field. Now if we keep on reducing, all the dipoles will rotate and become anti-parallel. They come in the other direction and become parallel to each other, not anti-parallel. In the other direction you will get the maximum value, and then further if you increase, the curve would be going like this. So this is all about the magnetization phenomena. Such kind of curve is known as hysteresis curve. Such kind of curve is known as hysteresis curve. This curve gives significant information about the magnetic behavior. If you are following this path in the curve, then it means it is a fresh magnetic material. But if we follow this path or this path, it means material has been magnetized sometimes ago in its history. It is not a fresh magnetic material. Now, this material exhibit spontaneous magnetization. These two should be same. मैं बना नहीं पाया, जितना ये वैल्यू होगी उतना ही ये होगी. Symmetrical होता है ये कर्व around the origin. ठीक है, you can make that. Now, this hysteresis phenomena results into a loss in the material. That loss is known as hysteresis loss. I will be talking about it later. So, this hysteresis loss is related with the width of the hysteresis curve. So, wider the hysteresis curve, more is the hysteresis loss. Narrower the hysteresis curve, less is the hysteresis loss. One more important thing which I would like to tell you, you see my dear friend, M is equal to chi m into h. If I differentiate it, dm is equal to chi m into dh. It means chi m is equal to dm upon dh. Chi m is mu r minus 1. And this dm by dh is slope of hysteresis curve. Slope of hysteresis curve. So the slope of hysteresis curve will give us permeability or susceptibility value. The slope of hysteresis curve will give us permeability or susceptibility value. Slope would be high when the curve is narrow and steeper. So the hysteresis curve narrow means high permeability. But if curve is wider and narrower, it means the slope is if the curve is wider and flatter, then the slope is less, and slope is less means magnetic permeability and susceptibility are less. And that is why the wide curve has more loss, because permeability is less means magnetization is less, so most of the applied energy is being wasted in the form of loss. Those losses will come into the form of heat. So I will be talking about them later. So this is all about the hysteresis phenomenon. This all has happened. Why? Because the dipoles were parallel. Now suppose we start increasing. So if we start increasing the temperature, then dipoles will start becoming random. And if dipoles start becoming random, then the value of spontaneous magnetization will decrease and this curve will become narrow. And that is the reason why in the ferromagnetic state, with increase in temperature, susceptibility increases, because curve become narrow means slope becomes high. Once you reach to Curie temperature, then all these dipoles become random, and all the dipoles become random, then material will become paramagnetic, and paramagnetic material shows y is equal to mx type of characteristic. So this curve will merge into a straight line. So you can write above Curie temperature, with increase in temperature, with increase in temperature, with increase in temperature, width of hysteresis loop, width of hysteresis loop decreases, width of hysteresis loop decreases, and above Curie temperature, this loop merges into a straight line. This loop merges into a straight line. This loop merges into straight line. This loop merges into a straight line. ठीक है जी? So let's write all this. आप इसको बना भी सकते हैं. You can draw it like this. This is M or B and this is H. So above Curie temperature, it will be looking like this. T greater than theta, theta is Curie temperature, and the material has become paramagnetic. It has become paramagnetic. It has become paramagnetic. एक एक तरफ का लिखते चलिए, यहां से लिखते चलिए. First you write this. मैं दिखा दूंगा पूरा, एक बार में पूरा आ नहीं रहा है, छोटा करने पर बहुत छोटा हो जा रहा है. कुछ भी रिपीट नहीं करेंगे। जिनको रिपीट करने की जरूरत है दूसरा वीडियो फिर से देख ले, क्योंकि 1 घंटे की एक्सप्लेनेशन रिपीट करने का कोई लॉजिक नहीं है। सो इफ यू वांट टू बी रिपीटेड एनीथिंग देन यू कैन वॉच द वीडियो अगेन। वीडियो इज अवेलेबल टू यू टू वॉच फॉर 2 times, so you can watch it. Do it quickly. First you draw the graph, that is more important. Draw everything related with the graph. Done? फर्स्ट वाला आपने बनाया ही होगा, सेकंड थर्ड। यस अनूप मलिक। डन। This is point. Okay, these magnetic materials are used to design core of a inductor or transformer. Inductor, you may have seen there is a structure like this. This is a core material. On that core material we wrap wires like this, we wrap wires, and a current starts flowing through this. So this core is basically magnetic material. This core is magnetic material, and ferromagnetic materials, being a very good magnetic material, are used to make the core. This device is known as inductor, and when several inductors are coupled to make a machine, that is known as transformer. So to design the core of inductor or transformer, we need magnetic material. We allow the current to flow in this wire, but we don't want any current in the core. Current should be flowing in the wire, not in the core material. If any kind of current flows in the core material, that will lead to the losses in the material, and we do not want to have losses, because if there are losses, those losses will reduce the efficiency of system. So let us try to see what kind of losses can be there in the core material. So next heading is core losses. Core losses. Magnetic materials are used. Magnetic materials are used in the designing of core of inductors and transformers. Core of inductors and transformers. Following two types of losses are observed in core material. First, eddy current loss. Eddy current loss. Second, hysteresis loss. Hysteresis loss. Following two types of losses are observed in the core material. तुम लोग पहले क्यों पिक नहीं लेते हो? पिक ही लेनी थी तो पहले क्यों नहीं ले लेते हो? देखो बेटा 10 लेक्चर हो गए हैं एंड this batch is going too slow as comparison to the other batches. Unnecessarily at the end I have to cut down few topics because जो भी आवर्स दिए गए हैं उनमें जितना भी टॉपिक कवर होगा उतना ही पढ़ाया जाएगा. सो आप चाहे जितना स्लो करवाना चाहो आप टॉपिक से कंप्रोमाइज कर लो, मैं एक ही टॉपिक को पूरा पढ़ा करके पूरा दिन पढ़ाता रहूं. इट हार्डली मैटर्स फॉर मी. ठीक है, क्योंकि बहुत ही स्लो राइटिंग स्पीड है. आइए फर्स्ट एडी करंट लॉस. एडी करंट लॉस. Actually, when this current flows, so the current is alternating, AC current. So since the current is alternating, so magnetic field which will produce that will also be alternating. So because of alternating magnetic field, a flux would be induced and that flux is changing with time. Faraday says that whenever there is change in magnetic flux, an EMF is induced. So that EMF is induced across the core material. The wire is like this, so this is the core. So EMF means voltage is induced across the core material. Since core is a metal, so if any EMF is induced, that will lead to flow of current. So a circulating current flows on the surface of core material. Such circulating currents are known as eddy currents. They are unwanted because we do not want any current in the core. So these unwanted eddy currents contribute a loss in the core material, and that loss is known as eddy current loss. So we can write due to change in magnetic flux density, an EMF is induced, across core material. An EMF is induced across core material. This induced EMF results into a circulating current, at the surface of core material. Such circulating currents are known as eddy current, and they contribute a loss in the core known as eddy current loss. They contribute a loss in the core known as eddy current loss. So this eddy current loss is given as P eddy, pi square B square T square F square rho into beta. This is B is magnetic flux density. This is B. T is thickness of core. F is frequency. Rho is resistivity. Beta is material constant. Now suppose we are wanting to reduce eddy current loss. We cannot reduce B. Magnetic flux density cannot be reduced because we are wanting to develop magnetic flux. So don't touch B. Pi and beta constant you cannot change. F, frequency. Frequency of a particular operation is generally fixed. So we do not have choice to vary it also. Now we have choice to change T and rho. So to reduce this loss, either thickness can be reduced or resistivity can be increased. We will be doing both to reduce this loss. If we use very thin layer, then there would be a problem. Of a very thin layer, mechanical strength will be very small. So when we wrap wire, this may break down. So we need a little bit strength in order to sustain the load, in order to support the wire. So we cannot reduce thickness very much, but we can use a method in order to overcome this problem. Let us suppose this much of the thickness is required. This is compulsory to get the desired mechanical strength. So instead of using single core, let's use a large number of thin sheets stacked together on the core. So instead of single core, we are using a number of thin sheets. Any particular sheet is T dash, thickness is T dash. T dash is very small to T. T dash is very small to T, right? Now, since eddy current flows on the surface, so it will flow in this surface and in this surface. In between these two cores, there is an insulating material. Suppose this is air. Generally, it's not air. Generally, this core is dipped into some insulating liquid. So, between these two layers, there is an insulator. So, this eddy current cannot go to this, cannot go to this. So, effectively, the material will have thickness this and this only instead of this. This way the overall thickness can be reduced and the losses can be minimized. Such cores are known as laminated cores. So instead of using a single core, use thin sheets stacked together and they will reduce the eddy current losses, and such cores are known as laminated cores. Second method is to increase the resistivity. So instead of using pure iron, use alloy. I told you alloys has higher resistivity than the pure iron. So we use basically silicon steel, where 5% of silicon is added into the iron. So when you add silicon into the iron, it will function like an impurity and it will scatter the electron, mobility will come down, conductivity will come down, resistivity will increase. So this way the resistivity of silicon steel is higher than the pure iron, and this will reduce the eddy current losses. So you can have, to reduce the eddy current loss, to reduce the eddy current loss, to reduce the eddy current loss, the first thing is to reduce eddy current loss, laminated cores are used. Laminated cores are used. Second thing is silicon steel, that is 5% silicon is added into iron. Silicon steel is used instead of Fe, iron. These two are the methods to reduce the eddy current loss. Please do it quickly. This is your eddy current loss. जल्दी से करें. Next is hysteresis loss. Next is hysteresis loss. Hysteresis loss. This is due to the width of hysteresis curve. So, hysteresis loss is directly proportional to the area or width of hysteresis loop. Wider the hysteresis loop, higher is the hysteresis loss. Narrower the hysteresis loop, lesser the hysteresis loss. Both of these losses will depend upon volume of the material also. Higher the volume, more will be the dipoles. So all those things will also affect. So these losses will depend upon volume of the material as well. So you can write P hysteresis is eta B to the power NF watt per meter cube. Per meter cube means it will depend upon volume of the material. Previous one also watt per meter cube, that will also depend upon volume of material. Eta is material constant. Material constant. N is an exponent, it is also a constant. Exponent, it is also a constant. B is magnetic flux density. B is magnetic flux density. B is magnetic flux density. And F is frequency. And F is frequency. Now you see, my dear friends, to reduce the hysteresis loss, the best way is to use a material which has narrow hysteresis loop. So if narrow hysteresis loop, hysteresis losses would be less. Such materials which are having narrow hysteresis loop, they are known as soft magnetic material. I would be talking later about soft and hard magnetic material. Just note down here. To reduce hysteresis loss, to reduce hysteresis loss, soft magnetic materials, soft magnetic materials are used. What are soft and hard magnetic materials? I would be teaching you later. Don't worry about that. अभी लिख लें सर. Yes, Gurdeep. These are the same laminated cores of which we use in the transformer. Dear, formulas directly तो नहीं पूछे जाते हैं, but questions related with formula they ask, because once they ask कि on what factor the hysteresis loss will depend, so they have written it depends upon magnetic field, it depends upon frequency, it depends upon volume of the material. So you see, only this formula would be telling you watt per meter cube means volume of the material. Per meter cube is nothing but volume. Frequency is there, and B is magnetic flux. It means it is indirectly depending upon the magnetic field. So they may not directly ask the formula, but they must be asking questions related with these formulas. Good. Next, these magnetic materials exhibit some beautiful character that is known as magnetostriction. Magnetostriction. Actually, when magnetic materials are put into the magnetic field, so magnetic field exert force on the dipoles. These dipoles are in the atoms. So basically that force is experienced by the atoms. And when atoms experience force, they may be displaced from their position. And because of displacement of atoms, some strain is induced in the material. So if there is any strain means change in dimension. If there is a strain in the material due to the application of magnetic field, this phenomena is known as magnetostriction. Okay? So when magnetic materials are magnetized, changes in dimensions are generally observed, and this phenomena is known as magnetostriction. This magnetostriction is responsible for a very important thing in the transformer. If you go to near about any transformer, you will find out that there is a noise like this, something like this. So this noise is known as humming noise, right? The reason for humming noise is this magnetostriction. Actually your cores are laminated on each other, stacked one to another each other, एक दूसरे के ऊपर stack करके बनाई गई हैं, and your magnetic field is alternating. So in the positive cycle, if expansion takes place, in the negative cycle compression takes place. So expansion, compression, expansion, compression, because of which these cores make friction on each other, and this noise is due to that friction. So this magnetostriction is responsible for the humming noise in the transformer. एक लाइन में डिफाइन कर लेते हैं. When magnetic materials are magnetized, then changes in dimensions are generally observed. Then changes in dimensions are generally observed. When magnetic materials are magnetized, then changes in dimensions are generally observed. This property of magnetic material is known as magnetostriction. This property of magnetic material is known as magnetostriction. Humming noise is responsible. Magnetostriction is responsible. Magnetostriction is responsible for humming noise in transformers. Magnetostriction is responsible for humming noise in transformers. लिख लें. इसकी अपोजिट फिनोमेना भी होती है. सपोज यू टेक अ मैग्नेटिक मटीरियल and you apply a uniaxial stress in the material. Let us suppose longitudinal deformations you are doing. So if you are applying sufficient mechanical stress and permanent deformation in the material will happen, then that permanent deformation will lead to change in orientation of the atoms, and hence orientation of dipoles will also change. And if the orientation of dipoles changes, magnetic property changes, magnetization changes, susceptibility changes. So because of the applied mechanical stress, if there is change in magnetic property, then this effect is opposite of the magnetostriction, and that is known as Villari effect. If there are my friends from electrical engineering, so this is the reason why you use cold roll grain oriented steel, CRGO steel, to design these magnetic cores. You do the cold rolling in a particular direction so that the domains get oriented in that direction and you get a higher value of magnetic property in that direction as comparison to the other direction. This is the reason of using CRGO steel. So you can write here Villari effect. Villari effect. Villari effect. Villari effect, it is converse of magnetostriction. It is converse of magnetostriction. Converse of magnetostriction. It is converse of magnetostriction. Longitudinal deformations lead to longitudinal deformations lead to change in magnetic permeability of material. Magnetic permeability of material. Longitudinal deformations lead to change in magnetic permeability of material along the direction of applied mechanical stress. Applied mechanical stress. Along the direction of applied mechanical stress. This is known as Villari effect. Villari effect. This is known as Villari effect. Abhishek, the region for the sound of high tension transmission lines is corona effect. So किसी इलेक्ट्रिकल के फ्रेंड को पकड़िए, वो कोरोना आपको समझा देगा. Not part of this syllabus, so not going to discuss that corona etc. Done? Good. So let us move on to the next material. Next is antiferromagnetic material. Antiferromagnetic material. Antiferromagnetic materials में these are the materials which contain anti-parallel arrangement of dipoles. These dipoles are equal in magnitude but anti-parallel to each other. So they will cancel each other and you will get zero spontaneous magnetization. So there is no spontaneous magnetization in these materials. If you apply magnetic field in one direction, so one side dipoles will get strong but other are opposing. So you will be getting very small value of magnetization along the direction of field, means susceptibility is small and positive value. These materials follow a very important equation, that is chi m is equal to c upon t plus theta n. This equation is known as Neal's law. This is known as Neal's law. Here C is Curie constant and theta n is Néel temperature. It is just like Curie temperature. Below this temperature your material will remain antiferromagnetic, but above Néel temperature it will become paramagnetic. हर एक material higher temperature पर it is going to become paramagnetic, because at higher temperature thermal energy would be very high. So all these dipoles, because of that thermal energy, will become random, and random dipole arrangement means paramagnetic. So these materials will also convert into paramagnetic after a certain temperature. That temperature is known as Néel temperature. Some popular example of this material are MnO, MnO2, FeO, etc. So these are generally metal oxides. You can write these materials contain anti-parallel arrangement of dipoles. Anti-parallel arrangement of dipoles which are equal in magnitude, which are equal in magnitude. Hence, spontaneous magnetization is zero. Magnetization is zero. These materials are having small and positive value of magnetic susceptibility. These materials are having small and positive value of magnetic susceptibility. These materials remain antiferromagnetic up to Néel temperature. And above Néel temperature they start behaving like paramagnetic material. They start behaving like paramagnetic material. Do it quickly. Good. Next, ferrimagnetic materials. ferromagnetic materials. Ferromagnetic materials. These materials also contain anti-parallel arrangement of dipoles, but they are not equal in magnitude. Because of anti-parallel arrangement, these dipoles will try to cancel each other, but since they are not equal in magnitude, so they cannot cancel totally. Hence, you will get non-zero value even in the absence of field, because they are not able to cancel 100%. So this non-zero value means spontaneous magnetization, and spontaneous magnetization means hysteresis curve. So these materials are behaving everything like ferromagnetic materials. The only difference is in ferromagnetic, all the dipoles are parallel, so you get a strong value of spontaneous magnetization. It means wide hysteresis loop. But in these materials, some are anti-parallel, so you will get a small value of spontaneous magnetization. It means curve is narrow. So these materials will behave like ferromagnetic, but they have narrow hysteresis loop as comparison to the ferromagnetic materials. When you increase temperature, at Curie temperature, all these dipoles will become random, and these materials will also start behaving like a paramagnetic materials. But one very important thing which need to be observed, these are generally oxides of two metals. The example of ferromagnetic materials are ferrites, and ferrites are generally oxides of various metals. So oxides means insulators, ionic materials. Ionic materials are insulators. So their resistivity is very high. And if resistivity is very high, eddy current losses would be negligible. So these ferromagnetic materials, in fact ferrites, are having negligible eddy current loss as comparison to the ferromagnetic materials. And hence they can be used to design core of the transformer in high frequency applications to reduce the eddy current loss because of their higher resistivity as comparison to the ferromagnetic material. Someone will say why only at high frequency? We can reduce the loss at low frequency also, so let us use them at low frequency. The reason is they are ionic materials. So ionic materials are brittle materials. It is very difficult to shape them, and if you difficult to shape them, it means their cost of production will become very high. So they become very expensive. That is the reason why we do not use them at low frequencies. But at high frequencies, we are not left with any choices. At high frequency, ferromagnetic materials will produce very high loss because core losses are directly proportional to frequency, basically square of the frequency. So at high frequency, losses will become very high. So to reduce those losses, we are not left with any choice rather than using these materials. So at high frequency, we will be using these materials as a substitute of ferromagnetic materials in designing up core of transformers या inductors. So please note down, these materials also contain anti-parallel arrangement of dipoles. Anti-parallel arrangement of dipoles. Anti-parallel arrangement of dipoles which are not equal in magnitude. Which are not equal in magnitude. Not equal in magnitude. Which are not equal in magnitude. Hence, these materials exhibit spontaneous magnetization and hysteresis curve. Spontaneous magnetization and hysteresis curve. The advantage of ferromagnetic materials, here ferrites. One more thing we can write. These materials remain ferrimagnetic up to Curie temperature, up to Curie temperature, and above Curie temperature, and above Curie temperature, they start behaving like paramagnetic. They start behaving like paramagnetic material, paramagnetic. The advantage of ferrites is their higher resistivity. The advantage of ferrites is their higher resistivity. The advantage of ferrites is their higher resistivity, because of which the advantage of ferrites is their higher resistivity, because of which they have lower eddy current loss, Hence, ferrites are used in designing of core of high frequency, inductors and transformers. The advantage of ferrites is their higher resistivity, because of which they have lower eddy current loss. Hence, ferrites are used in designing up core of high frequency inductors and transformers. Do it quickly. Do it quickly. Done? Right. Next. So, these were the 5 classification of the magnetic materials based upon presence of dipoles and their orientation. We can classify magnetic materials in another way. Classification of magnetic materials based upon width of hysteresis loop. Classification of magnetic materials based upon width of hysteresis loop. So magnetic materials can be classified broadly as two types. One, you see, this is M versus H, या B versus H. So one classification can be like this. One is this. This is narrow hysteresis loop. So such materials are known as soft magnetic materials. And here you have wide hysteresis loop. So such materials are known as hard magnetic materials. So based upon width of hysteresis loop, we can have two types of magnetic materials, soft and hard. You see, in the hard magnetic material, retentivity and coercivity is high. One thing which I forgot to tell you here, वैसे वहीं बता देते हैं, छोड़ो. This maximum value of the flux which a material can hold, that is known as retentivity, and the maximum value of field required to make retentivity zero, that is known as coercivity. So this amount of field is known as coercivity या coercive field, and this amount of magnetic flux जिसे spontaneous magnetization कह रहे हैं, that is known as retentivity. So you can first write here retentivity maximum value of spontaneous magnetization is known as retentivity, and coercivity, maximum value of coercive field, maximum value of coercive field is known as coercivity. Coercive field is the amount of field required to make spontaneous magnetization zero. ये दोनों टर्म डिफाइन कर लो, इनका यूज होता है कई बार. Now you see hard magnetic materials have high retentivity and high coercivity. So because of high coercivity, they are difficult to demagnetize. So they cannot be used for the high frequency signals where rapid magnetization and demagnetization is required. High frequency means rapidly positive, negative, positive, negative, positive, negative, like that. So rapid magnetization and demagnetization would be required, but because of high value of retentivity and coercivity, they cannot follow. So these hard magnetic materials are not suitable for high frequency application, but they can be used to make permanent magnet, because in permanent magnet, when we are making that magnet, we will bring it up to the saturation level and then we will leave the field. When field is left, still they are having a strong value of magnetization. So by using that residual magnetization, spontaneous magnetization, retentivity, by using that retentivity, they would be attracting the other materials. So these materials are best suitable to you to make permanent magnets. That's why sometimes hard magnetic materials are also known as permanent magnet materials. इनकी properties देखो, high retentivity, high coercivity, high hysteresis loss because of the wide hysteresis loop, but slope is less. So slope is less means permeability and susceptibility would be less. जनरली क्या होता है, सब कुछ हाई होने के चक्कर में लोग परमियाबिलिटी भी हाई लगा देते हैं. नो, परमियाबिलिटी इज व्हाट, स्लोप ऑफ हिस्टेरेसिस कर्व. ससेप्टिबिलिटी इज व्हाट, स्लोप ऑफ हिस्टेरेसिस कर्व. सो स्लोप फॉर द वाइड कर्व इज लेस and slope for the narrow curve is high. In other case, you see retentivity and coercivity are very small. So soft magnetic materials can be easily magnetized and demagnetized. So they can be used for the rapid switching. They can be used for high frequency applications. Like you want to use them in computers, you can use, because the speed of processor is in gigahertz. So for high frequency applications, we will be preferring these materials. One thing. Second thing, retentivity and coercivity are less, so they can be easily magnetized and demagnetized. Properties, if you see, low retentivity, low coercivity, lower hysteresis loss, but slope is high. Slope is high means susceptibility and permeability would be high. So let us write these facts. Hard magnetic materials first. Hard magnetic materials. Hard magnetic materials. These materials contain, these materials have wide hysteresis loop, have wide hysteresis loop. Hence, they cannot be easily demagnetized. These materials are used to make permanent magnets. Permanent magnets. Properties अगर देखें, so properties are high retentivity, high coercivity, high coercivity, high hysteresis loss, high hysteresis loss, low susceptibility and permeability. Low susceptibility and permeability. Examples: carbon steel, tungsten steel, alnico, aluminium, nickel, cobalt, Q-knife, copper, nickel, iron, etc. Please. Yes, Prateek. Done? Soft magnetic materials. Soft magnetic materials. Soft magnetic materials. These materials are having narrow hysteresis loop. These materials are having narrow hysteresis loop, and can be easily magnetized and demagnetized, Hence, these are used in high frequency applications. These are used in high frequency applications. इनकी प्रॉपर्टीज के बारे में अगर बात करें तो प्रॉपर्टीज लो रिटेंटिविटी, लो coercivity, लो hysteresis loss, narrow hysteresis loop है, so high permeability and susceptibility. High permeability and susceptibility. High permeability and susceptibility. Next is examples. इनमें ferrous silicon alloy, जो ने बताया था मैंने कि अप टू 5% तक सिलिकॉन ऐड करते हैं, अप टू 5% सिलिकॉन एडेड. देन फेरस nickel alloy. There are 3 alloys of iron and nickel, and all 3 are soft magnetic materials. Perm alloy, mu metal, it is also an alloy of ferrous and nickel, and super alloy. And then ferrites, etc. are examples of this class of materials. Ferrites. Please note down it. Done. So this was all about the chapter named as magnetic properties of materials. Up till now we have covered introduction, atomic structure, and chemical bonding. Crystallography, electric properties of materials, electric properties of materials, then magnetic properties of materials. These are the chapters which need sound conceptual knowledge. So we try to cover them in depth conceptually. इस साल जितने भी ऑनलाइन बैच हुए हैं उनमें इतना ही पढ़ाया है और उसके बाद मैंने वीडियो दे दिया. बट यू डोंट वरी, आई एम नॉट गोइंग टू वीडियो टू यू. I will be covering remaining topics also in your class, live cover करेंगे. But for the remaining topics you need to study theory book also. Notes are not sufficient because the remaining topics are very much theoretical in nature. What are the remaining topics? The first one is mechanical properties of material. इसे तो लाइव क्लास में नहीं कवर करता हूं और नहीं करूंगा, आपके भी बैच में नहीं करूंगा. मैकेनिकल प्रॉपर्टीज ऑफ मटेरियल्स. उसका रीजन ये है कि द स्टूडेंट्स फ्रॉम सिविल एंड मैकेनिकल ब्रांच नीड नॉट टू स्टडी दिस चैप्टर. दिस इज एक्चुअली द इंट्रोडक्शन ऑफ सोम. सोम में जो आप स्ट्रेस स्ट्रेन बिहेवियर ऑफ द मटेरियल पढ़ते हैं, it is just that topic. Even in theory book you will see that it is directly copied from your theory book of strength of material. So civil and mechanical people need not to study it. So I have not been told to teach it in the class because of the reason कि 50% से ज़्यादा क्लास को इसको नहीं पढ़ाना है. So electrical and EC people will feel that कि हमें तो पढ़ना पड़ेगा, हमारे तो सब्जेक्ट तो सोम है नहीं. सो फॉर देम a 2 hours video is made you have to watch that video, and it is a standard procedure I follow in all the batches. The same is followed in your batch also. This will not be taught live online. The chapter named as Mechanical Properties of Material. Civil and mechanical students need not to watch that video also. They need not to waste their 2 hours time, 2.5 hours, whatever is the video duration. You need not to waste your time because you have already studied SOM, and in depth you have studied all these topics which are part of this chapter. So you need not to study it. But EC electrical people will be provided a video today, and you have to watch that video so that you can understand this topic. Remaining topics I would be teaching in the class. Remainings are ceramics, polymers, composites, and phase diagram, and alloys. Alloys, I would be dealing only with the basics of alloys. Remaining you have to memorize from the theory book कि आयरन की कितनी एलॉय होती हैं, निकल की कितनी होती हैं, all those you have to memorize. But how the alloy is formed and what are the basic concepts related with phase diagram, those will be covered in the class. So these are the 4 topics which I need to cover in the class. Now this I am not going to cover. This will video, recorded video is provided. Recorded video will be provided. आज ही मिल जाएगा आपको. After the class it will be uploaded in your portal. See, so that is not live video, that is recorded video, especially for the purpose of the recording, especially for the EC and electrical students, not required for civil and mechanical. This topic need not be studied by civil and mechanical persons. So let's begin with the next chapter, that is ceramics. ऋत्विक इज आस्किंग सर जीएस के 6 सब्जेक्ट हैं, इसके बाद टोटल कितना टाइम लगे? इट डिपेंड करता है कि क्लास आवर्स कितने लगती है. 6 सब्जेक्ट मतलब रफली 150 आवर्स. सो इट विल डिपेंड अपॉन कि हाउ मच आवर्स आर फॉर द क्लास. सो रफली 150 आवर्स. Let's go for ceramics. Ceramic. This word is taken from a Greek word keramikos, which means burnt stuff. इसका मतलब होता है जला हुआ material, burnt stuff. Why these materials are known as keramikos? Why they are known as burnt stuff? Actually, these are generally the clay-based products. Potter's material is also known. So these clay-based products, when they are fired up to a very high temperature, they become very hard. So they achieve their hardness and strength when they are burnt. That's why these materials are known as burnt materials or keramikos. These are generally ionic compounds. Sohini Saha is saying that for EC that recorded video, by which name it will be uploaded? It will be uploaded with the same name, Mechanical Properties of Materials. With the same name it would be uploaded, or extra video, that may be the name. Whatever name they will give, I will tell you at the group, right? So focus on here. So keramikos, sorry, keramico लिख दिया मैंने, keramikos या burnt stuff. Most of these materials get their desirable properties when they are heated to very high temperature. That's why they are known as burnt material or keramikos. Leave it, not important. The important thing is that these are generally compounds between metals and non-metals. The bonding between metals and non-metals is generally ionic bonding. although there can be some covalent character as well. So even if it is a covalent bonding, it would be the polar covalent. Polar covalent means ionic plus covalent. So most of these materials will exhibit characters like the ionic materials exhibit. What were the characters of ionic materials? Ionic materials are hard, brittle, high melting temperature. They have very high melting temperature, they are hard and brittle, they are non-conducting of electricity. All these are the characters of these materials. So all these characters would be exhibited here as well. So whatever I taught you during ionic bonding, that is valid here itself. Okay. Primarily the bonding is ionic, but there can be covalent character also. It means there can be polar covalent compounds as well, right? So first of all, let us try to write these few points. If these are ionic materials, then there is no chance of being organic. They will be inorganic materials. So first point I am beginning with this: inorganic materials. Inorganic materials. Inorganic materials. Second point is, first, these are inorganic materials. Second point is, these are generally compounds between metallic and non-metallic elements. These are generally compounds between metallic and non-metallic elements. Atomic bonding is predominantly ionic. Atomic bonding is predominantly ionic, but there can be covalent character also. There can be covalent character also. That is covalent plus ionic bonding. So दोनों हो सकती हैं ionic bonding. It can be either purely covalent, it can be either purely ionic, or it can be covalent plus ionic, but most of these compounds will have ionic character, right? So inorganic materials, these are generally compounds between metallic and non-metallic elements. Atomic bonding is predominantly ionic, but there can be covalent character also, so covalent plus ionic bonding, right? These are generally classified in two broad categories. What are those broad categories? Ceramics. They are classified as traditional ceramics. Traditional ceramics. And then engineering ceramics. Then engineering ceramics. Yeah, these are also known as technical ceramics. These are also known as technical ceramics. So engineering ceramics are technical ceramics. Traditional ceramics are basically the clay based products. जैसे गांव में कुम्हार जो बर्तन बनाता है, China clay and all those, these kind of your tiles, your sanitary wares at the house, all these are the examples of. So these are mainly clay based products. So they are the mixture of several things, particularly clay, silica, all these are the components of these materials. So you can say that these are mainly clay based products. 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 The major constituents are of traditional ceramics are, the major constituents of traditional ceramics are, first is clay, second silica, third feldspar. Feldspar is basically hydrated oxide, like aluminum oxide, hydrated means water content is very high. So this works as a bonding agent for the other components, so that these all components can be easily given the desired shape. Engineering ceramics are relatively pure compounds. They are either pure oxides or pure carbides or pure nitrides, like that. So these are relatively pure compounds, pure oxides या carbides या nitrides, etc. The major constituents of traditional engineering ceramics are, the major constituents of engineering ceramics are, first alumina, that is Al2O3, then silicon nitride, that is Si3N4, then silicon carbide, that is SiC, and then zirconia, ZrO2, etc. इत्यादि. Please note it down. That video is not only for EC, that is for EC and electrical as well, for both of the branches, and that is the part of GS syllabus only, not for technical. For technical they will be providing separate. How is the tea? देखो टेस्ट करो. आज कितना टॉपिक कवर होगा उसके बाद आई विल बी टेलिंग यू कि हाउ मेनी डेज आर रिक्वायर्ड. Probably 2 या maximum 3. Depends upon how much topic I cover today. Noted. Good. Tea is hot. Yes, it is hot. So this is about the traditional ceramic. Before I proceed, I would like to discuss the crystal structure of ceramic materials. Since I said that these are mainly ionic materials, so I would be focusing to discuss the ionic packing theory. How does the ions are packed in the crystal? That is known as ionic packing theory. एंड या इसे ही हम सेरेमिक क्रिस्टल स्ट्रक्चर कह सकते हैं. वेरी इंपॉर्टेंट थ्योरी. सो मेनी टाइम्स क्वेश्चंस हैज बीन आस्क्ड फ्रॉम दिस चैप्टर. द रिपीटेड क्वेश्चन लास्ट 6 years में आई थिंक 3 times क्वेश्चंस हैज बीन आस्क्ड फ्रॉम दिस टॉपिक. सो बड़ा ध्यान से मुझे सुनिएगा. एंड एक्सेप्ट मी नो वन इज टीचिंग दिस आल्सो. Even it is in the syllabus of mechanical engineering, it is the syllabus of technical mechanical engineering, still people avoid it. So please focus mechanical person, you may get question in technical syllabus. Electrical and EC, the heading which I am going to teach you, that is in your technical syllabus also. This whole ceramic material is in technical syllabus also. So it is for paper 1 as well as for paper 2 both. Please study it thoroughly. मजा आ गया. हाँ, हमारे इवनिंग बैच के स्टूडेंट्स बता रहे थे कि कई लोग दिल्ली में बैठ करके फिर भी ऑनलाइन कर रहे हैं. भाई बड़े वाले मूर्ख हो अगर दिल्ली में बैठ करके ऑनलाइन कर रहे हो. जहां ऑफलाइन क्लासेस अवेलेबल हैं, देयर यू शुड नॉट गो फॉर द ऑनलाइन. देयर यू शुड अटेंड ऑफलाइन. Online is substitute of offline, but it's not the exact replacement. ये तो मजबूरी में कि जब ऑप्शन नहीं है then online. Otherwise offline does not have any real substitute. राजांशु इज आस्किंग सर टेस्ट करने के लिए ऑनलाइन बैच को बस पूछते हैं या ऑफलाइन बैच में भी पूछते हैं? नहीं, आई आस्क टू एवरीवन बट आई नेवर ऑफर टू एनीवन. गुरदीप जी कह रहे हैं सर जैसे ही आप हाउस द टी पूछते हो कैप्टन अभिनंदन का एडवर्टीजमेंट याद आ जाता है जो पाकिस्तान ने बनाया था. गुड गुड. चलिए, सेरेमिक क्रिस्टल स्ट्रक्चर. सेरेमिक क्रिस्टल स्ट्रक्चर. Sometimes in the examination he may be asking questions with this name, ionic packing theory. Ionic packing theory. कितना important है ये कैसे बताएं तुमको, जितना तुम समझ पाओ. It is extremely important topic. There is a high probability that you will be getting question from this topic. जल्दी फोटो लो. आइए, त्रिदिबा सुंदर सतपति इज आस्किंग ऑनलाइन बैच का एडवांटेज ये है कि आप 2 बार लेक्चर देख सकते हो फॉर डाउट क्लियरिंग, और ऑफलाइन का एडवांटेज ये है कि डाउट होगा ही नहीं तो क्लियर करने की जरूरत ही नहीं पड़ेगी. ठीक, और जरूरत पड़ेगी तो वहां क्लास के बाद टीचर अवेलेबल रहता है. व्हाट अबाउट सिविल, आशीष ने पूछा. सिविल वाले तो जितना मैं पढ़ा रहा हूं बहुत है, बस आपके लिए इससे ज़्यादा कुछ सोचना ही नहीं. आपका टॉपिक आगे आएगा, कल या परसों की क्लास में आपकी भी ब्रांच के टॉपिक डिस्कस करेंगे. लेट्स गो फॉर इट. ceramic crystal structure. As we know that ceramic materials are ionic materials, and these ionic materials are generally made of cations and anions. Although cations and anions are nothing, they are the charged atoms. When one electron is leaving, this becomes cation, and one electron is coming on the atom, this becomes anion. But for the simplicity of analysis, we are assuming that the whole crystal is made of cation and anion instead of atoms, right? We do not talk about atoms. Now here we will be talking about ions only. Now one moment. Here we are taking a strong assumption. That strong assumption is that these ions are hard and spherical. We are assuming it. Maybe in real sense they are not exactly spherical, but we are assuming for the simplicity of analysis. This I am not doing. This is the standard assumption. And in that standard assumption, what they do, they assume that these ions are hard and spherical. So let us first write these two things and then we would be moving forward. Alok Nathani is writing, sir, tea is hard and hot, I think. Actually, I use adrak little bit more, so thoda sa to hard रहती है. Let's go. For those ceramic materials, for those ceramic materials, for those ceramic materials for which atomic bonding is for which atomic bonding is for which atomic bonding is predominantly ionic, for which atomic bonding is predominantly ionic. The crystal structure may be thought of, the crystal structure may be thought of as being composed of electrically charged ions instead of atoms. These ions are assumed to be hard and spherical, These ions are assumed to be hard and spherical. Now, the packing of ions is governed by two characteristics. First, stoichiometry should be maintained. Stoichiometry should be maintained means the ratio of cations and anions should be according to the formula predicted according to the formula. Like if you have NaCl, then the ratio of cation and anion should be 1:1, so that overall crystal will remain neutral. Or if you have CaF2, then the ratio should be Ca2 plus and F1 minus. This should be equal to 1:2. This should be equal to 1:2. How did I come to know that this ratio must be followed? By the magnitude of charge. Overall crystal should be neutral. It means total positive charge must be equal to the total negative charge. So that is possible only if here is 2 plus and here is 1 minus. So for each calcium there must be twice fluorine, then only the crystal will become neutral. Similarly here 1 plus and 1 minus, so both of them should be equal, then only the crystal will become neutral. So the first condition for any stable structure is कि the crystal should be neutral, and this neutrality के लिए how many cations and anions are required, means what is the ratio of cations and anions in the material, that can be obtained from the magnitude of charge on each of the component ions. So the first criteria is magnitude of charge, that will decide ki how many cations are there and how many anions are there. So let us have a look. Let us have a look. Two characteristics of the component ions, two characteristics of the component ions, two characteristics of the component ions. In crystalline ceramic material, in crystalline ceramic material, influence the crystal structure, First, the first characteristic, the magnitude of electrical charge, the magnitude of electrical charge on each component ion, the magnitude of electrical charge on each component ion, Please note down the magnitude of charge on each component ion. This, what does this indicate? This indicates that for stable structure, the crystal must be electrically neutral. For a stable structure, the crystal must be electrically neutral. That is, all the cation positive charges, must be balanced by equal number of anion negative charges. For a stable structure, the crystal must be electrically neutral. That is, all the cation positive charges must be balanced by equal number of anion negative charges. Right? For example, in CaF2, for stable crystal structure, there must be twice F1 minus ions as compared to Ca2 plus ions, then only the structure would be stable, because it must be electrically neutral. And I have told you so many times, if it is not neutral, it cannot be stable. Suppose it is positive charge, it will attract negative and will make any compound, so will not remain this pencil. It cannot be stable. If it has negative charge, it will attract to any positive charge, will try to make a compound, so it will not remain stable. So it will be stable only if it is neutral. So for the neutrality from magnitude of charge on each ions, we would be judging with respect to cation how many anions are required. For each cation, how many anions are required, that we would be judging. So in CaF2, for a stable crystal structure, there must be twice F1 minus ions as compared to Ca2 plus ions. Please note it down. From here, quickly, those who have not written up till now, they may take a picture. Each and every sentence written here in this heading is important for you. Very much theoretical topic, so you would be getting questions theoretically. Nothing now numerical is left, nothing derivative is left. All the derivations, concepts has been done already. Now there is lots of theory. Second criteria. Now you got to know what is the ratio of cation to anion, means for each cation how many anions are there, you got to know. Then you are wanting to know how these ions are arranged. So if you recall, during ionic bonding I told you ionic bond is non-directional. So in each direction there should be equal strength of the bond. So that will happen only if for a cation as much possible as much anions are surrounding it. So how many anions are surrounding to a cation, this will depend upon their relative sizes. Sizes means their radius. याद हो तो मैंने ऐसे आपको बना करके समझाया था, इसीलिए मैंने कहा था that chapter is very important, the first chapter. I make something like this. This is the cation. So here was an anion, here was an anion, here was an anion, here was an anion. Cl minus, Cl minus, Cl minus, Cl minus. And I said that ki bond is in all the direction, this direction, this direction, and this direction. So ionic bond is non-directional bond. Non-directional bond means bond is equally strong in all the directions. So this is possible only for each cation there are as much possible as a number of anions. So how many anions can surround a cation? That will depend upon their size. Let us suppose these anions and this cation is very large, anions are little bit smaller. So more number of anions can surround them. So how many anions are surrounding a cation, that will depend upon their size. So second criteria is relative sizes of cations and anion. The relative sizes of cations and anions, the relative sizes of cations and anions. Rc is cation radius, it is cation radius. Ra is anion radius, Ra is anion radius. Rc upon Ra is cation to anion radius ratio, cation anion radius ratio, radius ratio. If you recall, I told you that cations are always smaller than the anions. It means Rc by Ra is always less than 1. ये भी question पूछा गया है एक बार. Once they have asked कि what can be the possible value of Rc upon Ra, out of the 4 options only one option was correct, and that was less than 1. So Rc by Ra must always be less than 1. Nishtha, I am unable to understand. Sir, I request you kindly to give some time. I need to take guidance from you. Yes, you can ask anything, and I have given you different channels to connect with me. You can connect with me at Telegram, and there you can ask your queries. हेमंत इज राइटिंग सर हम सिविल वाले इलेक्ट्रिकल ब्रांच को सबसे हार्डेस्ट ब्रांच मानते हैं. अरे नहीं, सभी ब्रांचेस डिफिकल्ट हैं. फॉर इलेक्ट्रिकल पर्सन्स सिविल में भी डिफिकल्ट, फॉर सिविल पर्सन्स इलेक्ट्रिकल में भी डिफिकल्ट. each branch is difficult if you do not study, and if you study each one is easy. सब फिजिक्स ही है. आप देखो, मैं इलेक्ट्रॉनिक्स इंजीनियर हूँ. आई टॉक अबाउट इलेक्ट्रिकल टॉपिक्स, आई टॉक अबाउट सिविल टॉपिक्स. दीज ऑल वी आर गोइंग टू स्टडी. दीज मटेरियल्स आर बेसिकली used in civil and mechanical engineering. So we talk about civil engineering things, we talk about mechanical engineering things. So if you study, all the things are same, they are not different. राइट सर, जीएस ऑफलाइन बैच में पहले ही हो जाता होगा ऑनलाइन से? नहीं नहीं, ऐसा नहीं है. अभी इवनिंग में मैं पढ़ा रहा हूँ ऑनलाइन बैच, ऑफलाइन बैच में. राइट, आइए. सो आर सी अपॉन आर ए, दैट इज नोन एज कैटायन एनायन रेडियस रेशियो. जनरली इसे सिर्फ रेडियस रेशियो लिखा हो तो भी उसका मतलब आर सी अपॉन आर ए ही होगा. इफ ओनली रेडियस रेशियो इट इज रिटन, इट आल्सो मीन्स दैट आर सी अपॉन आर ए. Stop writing, look at me very carefully. I would be making certain diagrams here. So by this symbol, this color, I am showing cation. We are assuming these cations are hard and spherical, right? And with this symbol, we are representing anion. So from white color, I am representing anion, and this color, I don't know, क्या होगा ये, गुलाबी, whatever is that. So with this color I am representing cation. I am making few diagrams to explain few things. Have a look. Let us suppose this is an anion, this is an anion, this is an anion, and this is an anion, and there is a cation between these anions like this. This is the cation, one structure. Then another structure here, a anion, another anion, another anion, another anion. Then here is a cation. This is a cation. Then again you have a anion, anion, this is a cation. One more diagram I would like to draw. That is here. Let us draw. Right, I am making few diagrams. Let us have a look for these diagrams and then I would be explaining the things. In the first diagram, you see all the anions which are surrounding a cation, they are in direct contact with that cation. What does it mean? Anions will repel each other, but cation will attract them. So if attraction force is stronger than the repulsion force, then bond will remain stable. But suppose anion repulsion force is stronger, then the atoms cannot come closer to the cation. And if they cannot come closer to the cation, then bond cannot be formed. Because in order to form the bond, these atoms should come closer to each other. These ions should come closer to each other. So here all the anions which are surrounding a cation, they are in direct contact with that cation. It means this repulsion of anion is not that much stronger as the attraction of cation anion. So we can say that this structure is stable. Similarly here, repulsion little bit stronger than this case, but still cation is able to attract these ions. That's why these all ions are touching each other. So if all these ions are attracted by the cation, it means there is a bonding, and hence the structure will be stable. This structure is also stable. But in this case, you see, anions are touching each other, but cation is not able to touch them. It means what? This cation wants to attract, anion, but as soon as this anions want to come closer to this cation, this is being repelled. And because of this repulsion, this anion is not able to touch this cation. So if this anion is not able to touch this cation, it means there is no ionic bonding between this cation and anion. So if anions which are surrounding a cation, they are not touching to the cation, it means directly there is no bonding between this cation and anion. You take this cation outside, they will not restrict you because they are not bonded with this cation, and hence the structure cannot be stable. So in this case, it is unstable. So one big point which we can withdraw is for stable structure, all the anions which are in surrounding with a cation, they must be in direct contact with that cation. स्टेबल स्ट्रक्चर होने के लिए किसी कैटायन के चारों तरफ जितने एनायन हैं वो उस कैटायन के साथ डायरेक्ट टच में होंगे, तभी स्ट्रक्चर स्टेबल होगा. देन ओनली यू कैन से दैट कि बॉन्ड हैज बीन फॉर्म्ड एंड अट्रैक्शन इज स्ट्रॉन्गर एंड दैट हैज बीन एबल टू ब्रिंग द एनायन क्लोजर टू द कैटायन टू मेक द बॉन्ड. So for stable bonding in these materials, the anions which are surrounding a cation, they must be in direct contact with that cation. That is why first two structures are stable, but the third one is not stable. From this we can withdraw one conclusion. If I take this atom, this ion as reference, then how many neighbors are there? 4. The number of nearest atom with respect to considered atom is known as its coordination number. So this condition of touching cation and anion can help us to calculate the coordination number, right? Now, whether they will touch or they do not touch, it will depend upon their relative size, their ratio of the radius. So let us try to understand how the size and coordination number are interrelated with each other. Have a look for this purpose. Here we have taken one anion, one cation, and all these 3 anions are touching to it. It means how many immediate neighbors are there? 3. So coordination number is how much? 3. Now let us try to calculate the relationship between the radius of cation and anion for this coordination number. So that can be determined purely from the geometrical consideration. This relationship we can determine only from the geometrical consideration. We are assuming these ions as hard and spherical body. So if I connect the center of these 3 spheres, this will become equilateral triangle. And if it is equilateral triangle, then this angle is 60 degree. So half of this angle, now I am putting a line. So this line is nothing, this line is nothing. What is this? RC, the radius of cation, and this is RA. So this line is RC plus RA, right? And then I am putting a projection here 90 degree and this. So this line is basically RA. So this angle is half of the 60 degree. So this angle is nothing but 30 degree. This angle is 30 degree. I can take this triangle to calculate the relationship in the ratio. So cos 30 degree is base upon hypotenuse. So RA upon RC upon RA. RC plus RA, not RC upon RA. From this, if we calculate the value of RC upon RA, for this we can calculate the value of RC upon RA, and that RC upon RA is the value of RC upon RA. If someone has calculated, you will find it 0.155. So it is 0.155. This is the value of RC upon RA, radius ratio. What we can conclude? We can conclude to get the coordination number 3, the relationship between RC and RA must be 0.155. Similarly, for 4, tetrahedral geometry will form. You can get the relationship for 4. For 6, hexagon type of geometry will be formed. You can calculate the value of radius ratio from that geometry. So this way, for different coordination number, we can calculate the value of radius ratio. And if we have calculated and tabulated all these values, so from that value of radius ratio, we can directly comment on the coordination number. That is the biggest advantage of this ionic packing theory. If you know the radius ratio, you can comment on the coordination number. So I would be talking about it, but before that, you please draw all this and note it. सबसे पहले आप यही draw कर लो, क्योंकि इसको छोटा करेंगे अभी तो बहुत simple हो जाएगा. So you please draw it. फर्स्ट ऑफ ऑल रिस्पेक्टिव सर, हम बोल सकते हैं कि जहां पर बॉन्डिंग होगी वहां पे स्ट्रक्चर स्टेबल हो. ऑब्वियसली डियर, टू स्टेबल स्ट्रक्चर यू कैन गेट, for stable structure there must be bonding. Without bonding the structure cannot be stable. Nista, you can send me in the personal message box at Telegram. There is option of sending me message in the personal message box also, so there you can share it. So many students are sharing their personal problem in the personal chat box. C is not stable, Pratik Hars. If structure C is not stable, then we cannot talk about coordination number. Coordination number, we are talking about crystals which are stable. So for this, we will not be talking about coordination number, right? Now you see, so I said that for different structures, we can calculate the coordination number. So I am making a table where the radius ratio and coordination number will be related with each other. So this is like this: RC upon RA, and it is Cn, coordination number. So you can have RC upon RA less than, this is less than 0.155, then it would be linear structure and coordination number will be 2. But suppose your radius ratio is equal to or greater than, you can say 0.155 to 0.225, then coordination number would be 3. Then coordination number will be 3. If radius ratio is 0.225 to 0.414, then coordination number is 4. And if 0.414 to 0.732, then it is 6, then coordination number is 6. And if it is 0.732 to 1, then it is 8, right? So more than 8 coordination number is not possible with the ionic compounds. Ionic compounds can exhibit a coordination number at max coordination number, that is 8. उससे ज़्यादा संभव नहीं है. So this is known as radius ratio rule. Basically, radius ratio and coordination number are interrelated with this table, that is radius ratio rule. This radius ratio for the different coordination number has been calculated from the geometrical condition and assuming hard and spherical ions. So these relationships are only approximate, they are not exact, because all these atoms cannot be 100% spherical. So all these results are approximate. But for the ionic compounds, they give the correct result, so you need not to bother about it. So in the ionic compounds, if you know the ratio of the Rc upon Ra, then you can directly comment about the coordination number of the material without doing anything, without X-ray and all that. You can directly comment about the coordination number. But if there is covalent character, then this rule is not valid. Because if there is a covalent character, then directional nature of bond will come into the picture, and due to directional nature of bond, lots of space will remain empty. So only radius ratio is not sufficient. Then you need the bond angle also to comment about the number of nearest neighbors. Here we do not use that bond angle etc., because bond is non-directional. But if it is covalent character, then bond must have certain angle. So we need to use that angle also along with the radius values. So only radius ratio will not be sufficient to comment about the coordination number of the covalent solids. So if there is a covalent character in the solid, then this ratio, this rule is not valid. For example, zinc sulfide, that is a very important compound, ZnS. Right? In ZnS, zinc is cation and sulfur is anion, but they make tetrahedral structure, just like diamond they make the structure. So the bond angle is 109.5 degree. If you see the ratio of zinc and sulfur, so according to that ratio is greater than 0.414, so coordination number should be 6. But when we see the structure, coordination number is not 6, it is only 4. Why they do not follow the radius ratio rule? The reason behind is zinc sulfide has covalent character and there is a directional nature of bond. So because of that directional nature of bond, this rule is not followed. So this rule is strictly followed by the ionic compounds. It is not followed by the covalent compounds. For the covalent compounds, along with the radius ratio, you need bond angle also to comment about the nearest neighbors. But here in the ionic compounds, just radius ratio is sufficient to comment about the number of ions surrounding a cation. It means to comment about the coordination number. Hope you understand this. If you get this, let us try to write all these things. इसको लिख लीजिए, फिर कुछ बातें यहाँ पर लिखते हैं. देखा जो ये ख्वाब तो धन्यवाद आलोक नैथनी. I am happy that you got the things. Yes, Karthik, Cn is coordination number. Coordination number is number of nearest neighbors. So catan I am taking as reference. So nearest neighbors would be enans. So enans, catan, these number of enans are nothing but coordination number. Cn I will be writing full form. Coordination number, that is nearest neighbors. Cn is nothing but coordination number. And coordination number I have already defined as the number of nearest and equidistant atoms with respect to any considered atom. So I take this catan as the reference, then number of enans will be the nearest, and that is known as coordination number. ऋत्विक, टाइम का क्या किया जा सकता है? जितना टाइम बेटा यूज कर पाओ, जितना भी है उसमें बेस्ट अपना करने की कोशिश करो. सिंस इट इज़ अ वेरी लेंदी सिलेबस, सो टाइम ना आप एक्स्ट्रा कर सकते हो ना मैं एक्स्ट्रा कर सकता हूँ. वी कैन नॉट स्ट्रेच द टाइम. सो वॉट एवर टाइम इज अवेलेबल टू यू, ट्राई टू रीड इन दैट टाइम. एंड ऑब्वियसली 8:30 to 9:30, 11 आवर्स के बाद तो कुछ टाइम बचेगा नहीं. सो अप टिल नाउ व्हेन द क्लास आर रनिंग, बी रिलैक्स्ड एंड डू द क्लास. ऐसा नहीं है कि सिर्फ 1 महीने 2 महीने में ही पूरी दुनिया बदल दी जाती है. दुनिया बदलने के लिए बहुत समय लगता है. सो एक बार पहले क्लास करके कंसेप्चुअल क्लैरिटी डेवलप कर लीजिए. देन आफ्टर द क्लास व्हेन यू विल गेट सफिशिएंट टाइम, पॉजिटिवली बैठ करके रिवाइज करिएगा. हो जाएगा, चीज़ें सब हो जाएगी. प्लीज़ नोट डाउन. मैं डिक्टेट कर रहा हूं, लिखने की कोशिश करें. द रिलेशनशिप बिटवीन कोऑर्डिनेशन नंबर, द रिलेशनशिप बिटवीन कोऑर्डिनेशन नंबर, द रिलेशनशिप बिटवीन कोऑर्डिनेशन नंबर, between coordination number, the relationship between coordination number and catan-anion radius ratio, and catan-anion radius ratio are based on geometrical considerations, and assuming hard spherical ions, So these relationships are only approximate. So these relationships are only approximate, and there are exceptions also, and there are exceptions also. मैंने बोला कि द रिलेशनशिप बिटवीन कोऑर्डिनेशन नंबर एंड catan-anion radius ratio are based on geometrical considerations and assuming hard spherical ions. So these relationships are only approximate, and there are exceptions also. For example, some ceramic compounds with Rc by Ra greater than 0.414. Look at the board. Some ceramic compounds with Rc by Ra greater than 0.414 exhibit coordination number 4, instead of 6 exhibit coordination number 4 instead of 6 instead of 6 फुल स्टॉप। थोड़ा एक दो बातें और लिखाना है, लिखेंगे जरा। अच्छा, मातोंज इज राइटिंग सर अनस्टेबल में anion touches each other, they don't repel. Are they keep on repelling, we do not bother about. If the structure is not stable, it means it does not exist, whether they repel or not repel. Why do we bother? We would be bother only about those things which exist in the nature, no? So if anion is not able to touch cation, it means it cannot be stable, and if it is not stable, it is not existing. If it is not existing, why should we study about that? Right, please note down few lines. The stable ceramic crystal structure, the stable ceramic crystal structure is formed when all the anions, stable ceramic crystal structure is formed when all the anions which are surrounding a cation, they are in direct contact, with that cation, they are in direct contact with that cation. They are in direct contact with that cation. Full stop. Next point. The coordination number, is related to the cation anion, radius ratio. Is related to the cation anion radius ratio. The coordination number is related to the cation anion radius ratio. Full stop. For a specific coordination number, there is a minimum RC by RA ratio. There is a minimum RC by RA ratio. There is a minimum RC by RA ratio for which this cation anion contact is established. For which this cation anion contact is established. This cation anion contact is established. This ratio may be determined. This ratio may be determined from प्योर ज्योमेट्रिकल कंसिडरेशंस, जैसे हमने किया है, दिस रेशियो मे बी डिटरमाइंड फ्रॉम प्योर ज्योमेट्रिकल कंसिडरेशंस, from pure geometrical considerations. लिखें जिंक ब्लेंड क्रिस्टल स्ट्रक्चर, जिंक ब्लेंड क्रिस्टल स्ट्रक्चर, क्रिस्टल स्ट्रक्चर. It is also known as spherulite, SPHAR, spherulite. मुझे स्पेलिंग ही नहीं आएगी, छोड़ो हटाओ. जिंक ब्लेंड क्रिस्टल स्ट्रक्चर. Sphalerite, yes, it's correct. Sphalerite structure. Actually, the name of the zinc blend ZnS, mineralogical term for the ZnS is sphalerite. That's why it is known as sphalerite structure. Example: such kind of structure is found in zinc sulfide, zinc tellurite, या SiC, etc. It is just like diamond cubic crystal structure, but the difference is in diamond all atoms are carbon atoms, all are identical. But here two types of atoms are participating, zinc and sulfur. Zinc is cation, so it would be smaller in size, and sulfur is anion, so it would be larger in size. So in a cubic unit cell, all the corner and face positions of the cube are occupied by the larger ions. Those are anions. And at the interior tetrahedral positions, there would be zinc atoms, that is cations. Anions cannot go the interior position because at the interior position space is very less, so only the smaller atoms can occupy, and those are cations. So cations occupy the interior tetrahedral position. Tetrahedral position means bond angle is 109.5 degree. So with each zinc there are 4 sulfur atoms connected in the structure. So coordination number would be 4. Although if you see the coordination number from radius ratio rule, then it should be 6, but it is not becoming 6. The reason is it is a covalent compound, and in the covalent compound directional nature in the bonding has come, which does not allow to accumulate as much as possible anions. So this is the reason why coordination number is becoming less. So you can write that in a cubic unit cell of ZnS, in a cubic unit cell of ZnS, all the corner and face positions, all the corner and face positions of the cube are occupied by sulfur atoms, and interior tetrahedral positions, are occupied by zinc atoms. Interior tetrahedral positions are occupied by zinc atoms. Hence, each zinc atom has 4 sulfur atoms as nearest neighbors. So coordination number is 4. Please note down. This is all about the zinc blende crystal structure. Write it quickly. Done. I am giving the name of few other structures, just the name is required, detail we do not discuss, but sometimes they ask the name, so you should be knowing the name of few other structures also, like NaCl. In NaCl the structure is known as rock salt type crystal structure. Basically, it is interpenetration of two FCC structures. Na make their FCC, Cl make their FCC, and you penetrate them. Whatever structure is developed, that is known as NaCl crystal structure. That is rock salt type crystal structure. Not required to be memorized. Perovskite crystal structure is found in BaTiO3. This is perovskite. Only the name is required, not the depth analysis required. Perovskite crystal structure. This is the structure found in BaTiO3. It is very important compound. Then MgAl2O4. MgAl2O4. In this material, spinel structure is found. In this material, spinel structure is found. So these are the few structures. Name of these structures should be known to you. जिंक ब्लेंड में 3 एग्जाम्पल लिखे हैं हमने. Mainly it is decided on the basis of ZnS, but identical structure is found in ZnT, SiC. They also exhibit the same structure as zinc sulfide, right? Please note it down. Shall we go ahead? आइए. Now we have studied the crystal structure of ceramics. Now we will be talking about the properties of ceramics. So these properties we are classifying from different engineering applications. So first of all, we would be talking about the electrical properties of ceramics. So first one is electrical properties of ceramics. Electrical properties of ceramics. Electrical properties of ceramics. Since these are ionic materials, so they do not have free electrons. Hence, they are electrical insulators. So we would be using them as electrical insulators. They will have high electrical resistivity. This is the first property they are having. Now, since they are ionic materials, so they have already plus and minus charge, means they have already electric dipole. When we apply electric field, bond will stretch and they will show the strong polarization. So these materials may have high dielectric constant also because of high polarization. So we can use them as a dielectric material as well. Ionic bond is the strongest bond, so the material can withstand very high value of electric field. It means it has high dielectric constant also. High dielectric strength also. It may withstand very high voltage applied across this material, that is known as dielectric strength. So it has high dielectric strength also. This has very low dielectric loss. Loss is said as कि we are not wanting to flow any kind of current in the material. We want that if we put this into the capacitor plates, then its negative charge should be at one plate, positive at another plate. There should not be any current flow inside this material. But no material is ideal. There must be few electrons even in the good insulator. So those electrons will be leading to a small amount of current flow, that is known as leakage current, and that will cause a heat loss. But in these materials, since there is a very strong bond, so chances of getting free electrons is very negligible. So they will have very small leakage current and hence they will have very low leakage loss, dielectric loss. So they are very excellent material from electrical insulation point of view, and that's why we use them in the electrical industry as insulator or dielectric material. So we can write 4 points, 4 important points. First one is high electrical resistance. High electrical resistance. High electrical resistance. This is the first point. Second point is high dielectric constant. Second point is high dielectric constant. Third point is high dielectric strength. High dielectric strength. High dielectric strength. And third point is low dielectric loss. Low dielectric loss. Fourth point is low dielectric loss. This is the fourth point. Now, we can classify ceramics in two broad categories. One, when we are using them for insulation purpose, and other when we are using them to make the capacitor, that is for dielectric purpose. I told you that material used for the dielectric purpose should have high polarization. High polarization means dielectric constant should be higher. So we are taking epsilon R12 as the reference. इसके पीछे कोई लॉजिक नहीं है, प्रैक्टिकली 12 को बना दिया गया. अब इससे कम अगर एप्सिलॉन आर की वैल्यू है, देन वी कैन नॉट यूज इट एज कैपेसिटर. वी कैन यूज बट वी डू नॉट प्रेफर टू यूज इट. देन वी वुड बी यूजिंग मटेरियल एज एन इंसुलेटर. But if epsilon r is greater than 12, it means polarization is very strong and we can use that material to make the capacitor. So let us classify ceramics from electrical application point of view. So ceramics are classified as ceramics. You have two classification. First one is ceramics with epsilon r less than 12, and second, ceramics with epsilon r greater than 12. These are the classification. Now you see, my dear friend, these materials are mainly used are mainly used as electrical insulators, are mainly used as electrical insulators. These materials are mainly used as electrical insulators. Some of the examples are popular materials. Examples are, first example is alumina, that is Al2O3. It is Al2O3. Second material is electrical porcelain, that is known as China clay, electrical porcelain. Third one is statite. It is basically the talcum powder which you use to make to look beautiful. वो सुबह सुबह जो गाल पे आप छोपते हो, that is statite, right? Basically talcum powder का जो main component है वो statite है. These are mainly used in designing of capacitors. These are mainly used in designing of capacitors. These are rutile based, rutile, that is TiO2. If you recall, I told you very high dielectric constant. Rutile based compounds such as BaTiO3, etc. If you see, it is BaO plus TiO2, that is BaTiO3. So this is the classification from electrical application point of view. Please start noting it down from here. This is related with the electrical properties of these ceramics. Done? You write this. Quickly. Right. Next one, mechanical properties of ceramics. Mechanical properties of ceramics. My friend, from EC and electrical, you will not be able to absorb this heading thoroughly as of now until you do not watch that video of 2.5 hours or 2 hours, whatever may be the duration. So here you just write it. As soon as you watch that video, each and everything will become clear. Civil and mechanical students, if you are not able to absorb this, then slap yourself and slap as hard as you can, right? So this is very easy thing for you. Easy electrical person, just please keep on noting down, right? You will be able to absorb it only if you watch that video which I would be providing you today. After that, you would be able to absorb it. So let us write the first heading. First property is strength. Since these are the brittle materials, इसी इलेक्ट्रिकल सिर्फ सुनते और लिखते रहें, अभी आपको समझ में नहीं आएगा। जब आप मैकेनिकल प्रॉपर्टी पढ़ लोगे तो आपको समझ में आएगा। वहां मैंने इजीली एक्सप्लेन किया है, 2-2.5 घंटे यही 7-8 पॉइंट एक्सप्लेन किए हैं। EC and civil mechanical, listen me. Since these are brittle materials, these are ionic, and in the ionic bonding I told you these are brittle materials. So for the brittle materials, compressive strength is good, but they cannot have a tensile strength. Brittle materials are poor in tensile strength. They cannot sustain very high tensile load. So you can write it. Ceramics are stronger in compression. Ceramics are stronger in compression, stronger in compression, stronger in compression than in tension. Ceramics are stronger in compression than in tension. Second point, hardness. Since they are brittle materials, so obviously they will have high hardness. High hardness. High hardness. Next, brittleness, ductility and malleability. Brittleness, ductility and malleability. Ceramics are brittle materials with negligible ductility and malleability. These are brittle materials. Ceramics are brittle materials, with very small ductility and malleability, with very small ductility and malleability. Ceramics are brittle materials with very small ductility and malleability. These are brittle materials with very small ductility and malleability. Fourth one. The fourth parameter is elasticity. Ceramics have linear elastic behavior, elasticity. You draw the stress strain diagram. If you draw the stress strain diagram, sigma versus epsilon, you will get linear curve like this. So ceramics have linear elastic behavior. भक्त हैं Hooke's law के, they follow Hooke's law. Ceramics have linear elastic behavior, linear elastic behavior. They have linear elastic behavior. Ceramics have linear elastic behavior. The next one is, after elasticity we will have corrosion, toughness देख लेते हैं, फिर corrosion. Toughness. Toughness is shock absorbing capability. Since they have linear elastic behavior, so they will have very less area under the curve. Suppose if they have plastic revision, then large area under the curve, and area under the stress strain curve gives you toughness. So ceramics are having very low toughness as comparison to the ductile materials. So ceramics have low toughness. Ceramics have low toughness. They have low toughness. यही इनकी एक बड़ी ड्रॉबैक भी है, बिकॉज ऑल अदर प्रॉपर्टीज आर गुड, बट दिस इज वन ड्रॉबैक, दे कैन नॉट सस्टेन, दे कैन नॉट विदस्टैंड सडन लोड, शॉक या इम्पल्स. सिक्स्थ वन इज corrosion resistance. Since they are very strong materials, so they cannot be easily further oxidized, so their corrosion resistance is very high. Ceramics have very high corrosion resistance. Ceramics have very high corrosion resistance. Corrosion resistance. Ceramics have very high corrosion resistance. Then the next one is, the seventh one is, after corrosion resistance we have creep we would be studying in thermal property, leave it. Then crack propagation. in any material, if stress is concentrated at a point, then crack will be developed on that point. So in ceramics also, cracks would be developed at the stress concentration points, but these cracks can propagate during tensile load. During compressive load, the material's strength is very high, so cracks cannot propagate. So you can write ceramics develop crack, ceramics develop crack at the stress concentration points, at the stress concentration points. Ceramics develop cracks at the stress concentration points. These cracks can propagate under tensile load, but cannot propagate under compressive load, Eighth, crack propagation, then failure. Apurva is saying that this is civil engineers. Next, all the topics are from civil engineering. Whatever chapters are left, they are from civil and mechanical engineering. Right. Next one, after crack propagation, failure. Since this is brittle material, so sudden failure will take place. So these materials fail under brittle mode. Ceramics fail under brittle mode. Ceramics fail under brittle mode. Ceramics fail under brittle mode. This is all about the mechanical property of ceramic materials. Let's go for the thermal property of these materials quickly. These all are the mechanical properties. Do it quickly, please. What I said, strength. These are stronger in compression than in tension. Then hardness, high hardness, brittleness. Ceramics are brittle materials with very small ductility and malleability. Elasticity, they have linear elastic behavior. Toughness, have low toughness. Corrosion resistance, very high corrosion resistance. Crack propagation, develop crack at the stress concentration points. These cracks can propagate under tensile load but cannot propagate under compressive load. Ceramics fail under brittle mode. Next is thermal properties of ceramics. Thermal properties of ceramics. Thermal properties of ceramics. Since these are ionic materials, so you do not have free electrons, and they are very densely packed. Between 4 anions, there is a small interstitial position that is also packed with cation. So there is very less possibility of atomic vibration. So they do not have good atomic vibration, as well as they do not have free electrons. So these are excellent thermal insulators. They have high melting point, negligible coefficient of thermal expansion, negligible thermal conductivity. So we can use these materials as thermal insulation purpose. We can use them to make furnaces. We can use them to make refractories. Refractories means the material which can be used to make a furnace. So we can use these materials to make furnace. They can withstand very high temperature. They can withstand sudden change in temperature. That is known as thermal shock. So they can withstand, because for the temperature they are the insulators. So they can withstand sudden change in temperature also. They will have very high creep resistance. Even at high temperatures they will not creep easily. So they will have high creep resistance also. So we can write these points. High melting point, high melting point, high melting point, then next one is low thermal conductivity and expansion. Low thermal conductivity and expansion. Low thermal conductivity and expansion. Then third, high thermal insulation resistance. Yeah, high thermal insulation you can write. High thermal insulation. High thermal insulation. And ceramics can withstand thermal shock without cracking. Ceramics can withstand thermal shock without cracking. Can withstand thermal shock without cracking, and also have resistance to high temperature creep, and also have resistance to high temperature creep. High temperature creep. Please note it down. So these are the thermal properties. घड़ी की सुइयां इशारा कर रही हैं कि now we should stop here. So ceramics is more or less covered. Few things are left to be discussed. That is the application of ceramics. That I will be teaching in the next lecture. Here, few things you have to study from the theory book in this chapter. First is silicate structure, that I have written over there in this chapter. As in the very beginning I told you, in some theoretical topics you have to take the help of theory book as well. So silicate structure you have to study from there. Then you have to study carbon. Carbon has three alloys: diamond, not alloys, allotrope, diamond, graphite and fullerene. This you have to study from the theory book. Then there I have written very objectively, because मुझे पता था कि ये theoretical चीज़ें मैं क्लास में नहीं पढ़ाऊंगा. So all those things has been written over there. ये मैं क्लास में कभी नहीं पढ़ाता हूँ, किसी भी ऑनलाइन ऑफलाइन कहीं नहीं पढ़ाता हूँ. So that you have to study from the theory book. So that has been written by me in the theory book. Then you have to study glass also. हालांकि इन सभी के बारे में थोड़ा थोड़ा हम लोग पीछे के चैप्टर्स में डिस्कस कर चुके हैं. Whatever is important that I have included either in the crystallography or in some other topics, but in-depth analysis of all these three topics from this chapter you have to study from the theory book. Theory book of basics of material science. Basics of material science. Chapter का नाम है ceramics. In that chapter you will be finding these three topics, so that you have to study from the theory book. Rest whatever is left I will be talking about it in the next class. Thank you very much. Have wonderful time. 2 more lectures are required to complete this subject. Roughly around 6 to 7 hours is required. So it means 2 more lectures. So tomorrow at 8:30 I will be meeting you, and then day after tomorrow, and then this subject will be completed. Someone has written, sir, for chapter 1 to 4 the class notes are enough. Yes. For the remaining till magnetic properties, class notes are sufficient. You know, वैसे देखो theory book का कोई substitute नहीं. अगर समय है तो GS में जितना पढ़ पाएं that's good. That will be additional for you, that will give you more information. But for 1 to till the magnetic property chapter you need not to much worry about the theory book. Notes are sufficient because the topics are conceptual, numerical in nature. Analysis is required, so that I have done in the class. But here onwards lots of theory is required, lots of data is required. So for that purpose you have to refer for the few topics in the book. I would be telling you कि what you have to study from the book. So from this chapter, these are the topics which you have to study from the book, and whatever you have to study from the notes that I have told already. So tomorrow we will be meeting to complete this topic, as well as tomorrow I will be starting with a very important topic that is known as polymers. So tomorrow's target is these two topics, ceramics and polymers, and if time permits, we'll start composite. If do not permit, then we'll start composite in the next lecture. Thank you very much. Mechanical properties of material for the students of EC and electrical will be uploaded by the evening. I will be telling to the team to upload it as early as possible. Thank you very much. Have a wonderful time. We'll be meeting you tomorrow at 8:30 a.m.